Almost done. Question 63. This is actually kind of a fun little problem. We're asked to integrate this expression, sine of 100x over sine of x, from 0 to pi. So I guess your first instinct is probably to use the evaluation theorem. Unfortunately, I don't know the antiderivative of the integrand here, sine of 100x over sine of x. That's too bad, because that's kind of our standard way of evaluating definite integrals. So what can we do instead? Well, maybe if we analyze the integrand a little bit, we'll be able to better understand what's going on with this function. Unfortunately, I don't know what the graph of sine of 100x over sine of x looks like. So maybe instead we can kind of analyze the components. Let's take a look at the graph of sine of x and the graph of sine of 100x independently. So first, low-hanging fruit, the graph of sine of x. If you're taking this test, you're probably pretty familiar with what that looks like. I'll sketch it from 0 to pi because that's all we're interested in for this question. All right, that was easy enough. What about the graph of sine of 100x? Well, I'm not going to actually sketch that, but the idea is it looks just like this, except I'm going to compress the graph horizontally by a factor of 100. So instead of doing half of one full revolution when it goes from 0 to pi, we do 100 halves of one full revolution. In other words, we're going to squeeze 50 full revolutions in between 0 and pi. I'm not actually able to draw that, so you'll have to use your imagination a little bit, but the graph would look something like this. What we're going to do to evaluate this integral is take advantage of some symmetry. So if I sketch the line at x equals pi over 2, we have some nice even symmetry going on here. The graph to the right of this line is just a reflection of the graph to the left of this line. However, if I do the same thing over here, something different happens. What we're going to want to exploit is the fact that this graph in green does 1/4 of a full revolution between 0 and pi over 2. So since this graph in purple is this graph in green compressed horizontally by a factor of 100, instead of doing 1/4 of a full revolution, it'll do 1/4 of 100 full revolutions. What I'm saying is between 0 and pi over 2, this graph has done 25 full revolutions. Full being the operative word here, because after we complete a full revolution, we're back to the midline. So unlike this graph that has a height of 1 at x equals pi over 2, this graph is going to have a height of 0 at x equals pi over 2. And that'll end up being really important. The fact that we're starting a new revolution at pi over 2 means this graph is going to have odd symmetry. The graph to the right of pi over 2 is a reflection of the graph to the left of pi over 2, not over this line at x equals pi over 2, but over this point at pi over 2, 0. The fact that this graph in green has even symmetry and this graph in purple has odd symmetry, when we consider the midpoint of our bounds of integration, will allow us to evaluate the definite integral really easily. Maybe it's easier to see if we first do a u substitution. Our goal is to shift these two graphs pi over 2 units to the left. That'll put this line and point of symmetry on the y-axis, which will make our analysis a lot easier to see. The way we do that is we let u be equal to x minus pi over 2. If u is x minus pi over 2, then x is equal to u plus pi over 2, and du is equal to dx. With these substitutions, the integrand becomes the sine of 100 times u plus pi over 2 divided by the sine of u plus pi over 2. Our dx changes into a du, and our bounds of integration, which used to be written in terms of x's, can be rewritten in terms of u's. So I'm going from 0 minus pi over 2, in other words pi over 2, to pi minus pi over 2, in other words pi over 2. With these substitutions, we can redraw our axes, but instead of plotting along the x-axis, I'll plot along the u-axis. And instead of sketching y equals the sine of x, I'll sketch y equals the sine of u plus pi over 2. If you recognize this as a horizontal transformation, we're just taking the graph of the sine of u and shifting it pi over 2 units to the left. So this point that used to be at 0 is now over here at negative pi over 2. And this point that used to be at pi is now right here at positive pi over 2. Here's my graph. I can do the same thing for this disaster of a graph in purple. This is the u-axis. I want to sketch the graph from negative pi over 2 up to positive pi over 2. This graph will look identical to this graph, except the region up here pictured from 0 to pi will be pictured down here from negative pi over 2 to positive pi over 2. So between negative pi over 2 and the origin, I have my 25 full revolutions. I go through this point at the origin, and I have 25 more full revolutions between the origin and pi over 2. It's hard to see, but the important characteristic is that we go through the origin here, and that, in the symmetry of the sine graph, makes this an odd function. You may remember that in an odd function, f of negative x is equal to the negative of f of x, as opposed to an even function, where f of negative x is just equal to f of x. The integrand in this problem is the quotient of an odd function and an even function. But the nice thing about the quotient of odd and even functions is they're always either odd or even functions. And if you're taking the quotient of an odd function and an even function, you always end up with an odd function. Right, you can prove that to yourself pretty quickly. We've got this function, maybe we'll call it h of x, and it's some odd function, maybe I'll call it o of x, divided by some even function, e of x. To figure out if h of x is even or odd, I want to consider h of negative x. That's just going to be o of negative x divided by e of negative x. But since o is an odd function, o of negative x is the negative of o of x. And since e is an even function, e of negative x is just e of x. What I have written here is the negative of o of x over e of x. In other words, negative h of x. H of negative x is equal to the negative of h of x. So h of x must be an odd function. What I'm saying is an equivalent formulation of this question is integrate from negative pi over 2 up to positive pi over 2, some odd function. The specific odd function in question being this mess down here. Well, that's great news, right? Anytime you're integrating an odd function between points that are symmetric about 0, the answer is always just going to be equal to 0. Right? The picture to have in mind is that if I have some odd function, the height on one side completely determines the height on the other side. If this is what the right side looks like, this, give or take, is what the left side looks like. Because the heights are always going to be opposite on either sides of the y-axis, this area would cancel out this area would cancel out this area, and so on. So if I'm evaluating from any point, maybe I'll call it negative a, up to the opposite of that point, the areas on one side are always going to cancel with the areas on the other side. The definite integral will just be equal to 0. The answer to this question is just 0. The trick is to take this function, shift it pi over 2 units to the left so that our bounds of integration are symmetric about the y-axis, and realize that doing so would give us an integrand that's the quotient of an odd function and an even function. As long as you know that the quotient of odd and even functions is odd, you realize that the question is just asking you to integrate from negative pi over 2 to pi over 2 an odd function. You don't have to worry about what the odd function is. You automatically know that this definite integral is going to be equal to 0. Kind of cool.